Summary of analyzing graphs of f prime of x and f double prime of x. So here's a summary of important information that is needed to begin interpreting the graph of f prime of x and f double prime of x. So needless to say, this information should be memorized. Given the graph of f prime of x, if f prime of c equals 0 or is undefined, then c is a critical point of f. If f prime is greater than 0, f is increasing. If f prime is less than 0, f is decreasing. If f prime is increasing, the original graph of f is concave up. If f prime is decreasing, then f is concave down. If f prime of c is a local min or max of f prime, then cf of c is an inflection point of f. So any local min or local max on the graph of the derivative is an inflection point on the graph of the original function. And finally, if f prime changes from positive to negative at x equals c, then f of c is a local max. And if f prime changes from negative to positive at x equals c, f of c is a local min. So the last two statements are the first derivative test for critical points. Now, given the graph of f double prime of x, if the second derivative is positive, f is concave up. If the second derivative is negative, f is concave down. If the second derivative at c equals 0 and the second derivative changes sign at c, then cf of c is an inflection point on the graph of f. And if c is a critical point of the original function, and if the second derivative at c is positive, then f of c is a local minimum. And if c is a critical point of f of x and f double prime of c is negative, then f of c is a local max. So the last two statements are a summary of the second derivative test for critical points. So assume you're given the critical point c of the original function and the graph of the second derivative. If the second derivative is positive, then the original function evaluated at c is a local min, and if the second derivative is negative, f of c is a local max. Alright, first example, let the following be the graph of f prime of x. So this is a first derivative graph. The first thing we want to do is find the x values of the critical points of f. So we need to remember that critical points is where the derivative is 0 or undefined. So if this is the graph of the first derivative is 0 at any zeros or x-intercepts of the function. So my two x-intercepts here are 3 and 5. So the x values of the critical points are x equals 3 and x equals 5. Now, find intervals of increasing and decreasing of f. So this is the graph of f prime of x. So if we want to know where f is increasing, we want to know where f prime is positive. So f is increasing on the interval from negative infinity to 3 and from 5 to infinity. So from negative infinity to 3, this graph is positive or above the x-axis. So the first derivative is positive or above the x-axis from negative infinity to 3 and 5 to infinity, which means that f is increasing on those intervals. And so f is decreasing where f prime is negative, which means below the x-axis. So that happens on the x interval from 3 to 5. Now, the next part, find the x values of the local minimums and local maximums of f. Well, local mins and maxes can occur at critical points. So 3 and 5 are our two critical points. So I need to decide if each one is a local min, local max, or neither. So at 3, as I move from left to right, on the left side of 3, the derivative f prime of x is above the x-axis. So here we have above the x-axis to the left side of 3, and then below the x-axis on the right side of 3. So that means f prime changes from positive to negative. Well, if f prime changes from positive to negative, then f changes from increasing to decreasing. So by the first derivative test, f of 3 would be the local maximum. but it says find the x value of the local min and local max. So my local max is at x equals 3, and my local minimum is going to happen at x equals 5. So let me go ahead and erase some of what's here right now. So 5 was my critical point, and as I move from left to right, first I am below the x-axis to the left of 5, and then I switch to above the x-axis. So I go from below to above, or negative to positive, on the graph of f prime of x, which means f of x changes from decreasing to increasing, and that switch happens at x equals 5. So a local minimum occurs at x equals 5. So now the next thing we want to do is find intervals of concavity. So I'm going to erase everything that I have here. So what I know is that the original function is concave up where f prime is increasing. So now I want to look at this graph and determine where is this graph that I'm looking at, f prime of x, increasing. So from left to right, the y values are getting bigger. So this graph is increasing on the x interval from 4 to infinity. So this graph here, f prime of x, is an increasing function from 4 to infinity. So find intervals of concavity for f. So we have concave up, f is concave up, from 4 to infinity, where f prime is increasing. And then f is concave down, where f prime is decreasing. So that is over here, from negative infinity to 4. So where f prime is decreasing. So what I'm going to go ahead and do is write the reason why. So f prime's concave up on 4 to infinity because f prime is increasing, and here because f prime is decreasing. Local max at 3 because f prime changed from positive to negative, and here at 5 because f prime changed from negative to positive. We had f is increasing because f prime was greater than 0, and decreasing because f prime is less than 0. And the critical points occur where f prime equals 0. So here's the reasoning why. Here's the justification or the explanation. And so now finally, find the x values of the inflection points of f. So inflection points is where there's a change from concave down to concave up, or concave up to concave down. Well, I can look at these intervals of concavity and see that the x value, where I switched from concave down to concave up, was 4. But it's also true that at 4, that was a local minimum of the graph of f prime of x. So local minimums and local maximums on the graph of the derivative are inflection points on the original function, because when I'm decreasing on f prime, the original function is concave down, and then when I switch to increasing on f prime, the original function switches to concave up, and that switch happened at a minimum value at 4. So there's an inflection point. The x value of the inflection point is 4 because f prime changed from decreasing to increasing. From decreasing to increasing. But it could have also been from increasing to decreasing because that would have been a change in concavity. So this is all about having the concepts memorized. This is really the first derivative test here. This is by definition of concavity. This is the relationship between f and its derivative, and increasing and decreasing, positive, negative, the definition of a critical point, but really applying the concept and understanding it given the graph of the derivative. So this concept comes up over and over and over again, analyzing a graph. Alright, again, let the following be the graph of f prime of x. So this graph goes on forever. This is the graph of f prime of x. And we want to find the x values of the critical points. So again, we're looking for where the derivative is 0 or undefined. So this derivative is 0 at -2 and at 1. So the x-intercepts are -2 and 1. Find intervals of increasing and decreasing of f. So f is increasing where f prime is positive. So f prime is positive from 1 to infinity. So this graph is above the x-axis from 1 to infinity. because f prime is greater than 0. So this graph, the original graph of f, is decreasing, where this graph is below the x-axis. So this graph is below the x-axis from negative infinity to negative 2, and from negative 2 to 1. So I have to make sure and exclude negative 2, because at negative 2, the derivative is 0, not less than 0. So this is because f prime is strictly less than 0, not less than or equal to 0. Now the next part, find the x values of the local minimums and local maximums. So local mins and maxes occur at critical points. Our critical points were negative 2 and 1. Well, at negative 2, my derivative, as I move from left to right, my derivative was a negative, and then as I switch to the other side, the right side of negative 2, I stay negative. So a change from negative to negative means that there's neither a local min or local max at negative 2. But at 1, my other critical point, as I move from left to right, I'm first below the x-axis, or negative derivative, and then I switch to positive derivative above the x-axis. So a change in the derivative from negative to positive means a change in the original function from decreasing to increasing, meaning there's a local minimum. So at x equals 1, there's a local min because f prime changes from, so it goes from negative to positive. And we don't have to say anything about what happens at negative 2 because it's not a local max or a local min. Now, find intervals of concavity of f. So, f is concave up, so we're going to have f is concave up, and here f is increasing, f is decreasing. So f is concave up, where f prime is increasing. So this graph of f prime is increasing from negative infinity to negative 2, so negative infinity being over here, not down here, so we work from left to right on the x-axis. So from negative infinity to negative 2, and here's another interval of increasing from 0 to infinity. So remember, on the x-axis, so from 0 to infinity. F is concave up because f prime is increasing. And then we have that f is concave down, where f prime is decreasing. So that happens on the x interval from negative 2 to 0. And again, because f prime is decreasing. So now finally, find the x values of inflection points. So what I'm looking for are any minimums or maximums on the graph of f prime of x. So right here, I have a local maximum, and right here, I have a local minimum. So I have a change in f prime from increasing to decreasing. So a change in f from concave up to concave down. And here, I have a change in f prime from decreasing to increasing. So a change in f from concave down to concave up. So the x values where that happened are negative 2 and 0. So x equals 0 and x equals negative 2 are inflection points of f. And again, because f prime changed monotonicity. So from either increasing to decreasing or decreasing to increasing. Now here's one thing I really want you to notice, is that in all of these problems, it just said find the x values. So first, we cannot find the actual function values. We cannot find the y values because this is a graph of f prime of x. So nowhere on here are we reading the y value because that corresponds to the y value of f prime, not f of x. So typically when we're asked for the local maximum, we give the y value. But pay close attention to the fact that it said find the x values of the local mins and local maxes. So if it said find the y values, we would be restricted to just putting f of 1. So I would not go to this graph and say 1, 0. That's not the case. I want the actual y value on the original function, which I don't have. So that's why on these problems they're just asking for the x intervals and x values because that's all we can provide. Furthermore, these particular problems don't have explain next to them, but you can bet that my test and the AP test will say explain, that you will need the justification, the whys. Why is this value the local min or local max? Why is this where f is concave up or concave down? The justification is always required, and it has to be specific. So a reminder that you can never use the word it, ever. Alright, now let's move on to an example where we're given the graph of the second derivative. So this function is now f double prime of x, the second derivative. And I want you to notice that we can find far fewer pieces of information about the original function given the second derivative. So given the first derivative, we can find a lot more than given the second derivative. But let's figure out what we can find from the second derivative. We can definitely find intervals of concavity of f. So we can find where f is concave up and where f is concave down on the graph of the second derivative. So when the second derivative is positive or above the x-axis, f is concave up. So f is concave up from negative infinity to 3 and from 5 to infinity. And f is concave down where the second derivative is negative or below the x-axis, so that only happens from 3 to 5. And the reasoning or the justification is because on this one, f double prime is greater than 0, and here because f double prime is less than 0. So now find the x values of the inflection points. We want to know where the original function changes concavity. So remember, inflection points or possible inflection points is where the second derivative is 0 or undefined. So 3 and 5 are my candidates for a second, for my possible inflection points, or my inflection points, 3 and 5. So I want to make sure that the original function changes concavity. Well, f double prime from left to right starts out above the x-axis to the left of 3 and then switches to below the x-axis to the right of 3. So f double prime changes from positive to negative at 3. So f changes from concave up to concave down at 3, making 3 an x value of an inflection point. So x equals 3 is one of the inflection points of f. And x equals 5 is as well because f double prime from left to right changes from negative to positive. So f changes from concave down to concave up. So that change in concavity means 5 is an inflection point. So x equals 3 and x equals 5 are inflection points of f because concavity changes at each. Because concavity changes. So f double prime switches sign at these values. So you want to make sure and justify why does concavity change given the graph of f double prime, not just that concavity changes. Now this last part, suppose 2 is a critical point of f. So they're letting us know that x equals 2 is a critical point of f. Determine if the graph of f has a local min or local max at 2. So on the graph of the second derivative, if I know that f double prime of 2 were, let's say, positive or greater than 0, then that would mean that f of 2 is a local min by the second derivative test. So if the second derivative at 2 being a critical point, is positive, then the original function at 2 would be concave up. Well, a concave up graph has a local minimum. So what I need to decide is this the case? Is the second derivative at 2 positive or is the second derivative at 2 negative? So here's 2 right here. This is the graph of the second derivative. So at 2, the second derivative is positive. 3 is the output value. 3 is a positive number. So the second derivative at 2 is positive. So this is exactly the case. F double prime of 2 is greater than 0. So f of 2 is a local min by the second derivative test. So there's a local min at the x value 2. I don't know what it is. It's f of 2, whatever f of x is, but I know by the second derivative test there's a local minimum at x equals 2. Alright, final example. Again, we have a graph of f double prime of x. Find intervals of concavity of f. So where is f concave up where is F concave down? So F is concave up where F double prime is greater than 0 or above the x-axis. So this graph is above the x-axis from -3 to 0 and from 4 to infinity. So because F double prime is greater than 0. And F is concave down where F double prime is negative or below the x-axis. So from -infinity to -3 and from 0 to 4 because F double prime is less than 0. Now, the next one. Find the x values of inflection points of F. So inflection points, or possible inflection points, is where the second derivative is 0 or undefined. So the zeros, the x-intercepts, are -3, 0, and 4. And all of these are going to be my actual inflection points because concavity changes at each of those values. So I have a change in F double prime from below to above, so concave down to concave up. Here from above to below, so F changes from concave up to concave down, and below to above, so concave down to concave up. So x equals -3, 0, and 4 are all inflection points of F because F double prime equals 0 at each, and F double prime changes sign. So there's no one particular correct way to give your explanation. You just need to give a thorough explanation and cite each part of why that is the answer. So it can't be a vague justification, it has to be very specific. We not only need to say because the second derivative is 0, because that only makes them possible inflection points, we also need to say the second derivative changes sign. Now, an example of the second derivative not changing sign would be if, let's say, the graph bounced off. So at 4, let's say the graph kind of just touched and bounced off. Well, then 4 would be a possible inflection point, but not an actual inflection point. So that would be the difference in why you have to go all the way in your explanation and say that F double prime changes sign. And now finally, the same question as the previous example. Suppose 2 is a critical point of F. Determine if the graph of F has a local min or max at 2. So what's going on at the second derivative at 2? So at 2, if I go to the second derivative, that's a negative value, right? Some negative quantity. So F double prime of 2 is less than 0. So by the second derivative test, at x equals 2, there is a local max. So why a maximum? If the second derivative is less than 0 or negative, the original function's concave down would imply there's a maximum point. So that's understanding the concept of the second derivative test. So that's it for this topic. What I will say is that this topic shows up all over the place on the multiple choice, and questions just like this appear on the free response portion of the AP exam, and they definitely require the justification. Interpreting graphs is something that the AP test finds that is weakest on students. It had an average score of 2 out of 9 on last year's exam. So this is a topic that I will stress a lot heavily on quizzes and on tests, because if it's a weakness on their behalf, they're going to keep asking it until students get better and better at it. So the summary of important information at the beginning needs to be ingrained in your brain by the time you show up to class.